Well, good day, everyone. Uh, Today I'm going to talk about specifically aluminium and steel. I was originally going to call this lecture metal alloys, but since we're more concerned, I think, with structure, with using metals structurally, of course there are lots of metals that we use in the construction industry, more often for cladding and detail, of course, such as zinc and brass and aluminium as well for cladding, of course. But specifically I want to talk about the use of these materials structurally. And again, I hate to repeat myself, but I don't like to read from presentations, but I'm going to read this just to sort of ram it home to begin with. So aluminium is a softer and easier to cut than steel, more malleable and elastic, and therefore can create shapes that steel cannot. More deeper and intricate extrusions, especially for components with deep and straight surfaces. So of course you'll be familiar with the use of aluminium as, making window mullions and enclosures for double glazing systems and so on and so forth, because you can get the very sharp, fine, straight edges at a much smaller scale than you can with steel. Steel is tougher and more resilient over long periods of time, but as it says there, you cannot deal with it as exactly as you can with aluminium. Nevertheless, steel is harder and it's less likely to deform under loads, but it's heavier, of course, and denser, typically 3 times heavier, 2.5 times denser than aluminium, which means that there's always a trade-off. Aluminium tends to be it's more there's more of it on the planet now, and it's easier, if you like, or cheaper and less environmentally, has a smaller environmental impact to mine than does steel. Therefore, probably most of the steel that we will use in the construction industry in the future will be recycled rather than taking iron out of the ground and using the Bessemer process to turn iron ore into steel and processing it even further as we do. Nevertheless, let's just have a look at the way the systems do work. Generally speaking, with these materials, most of what we use in the construction industry, certainly for framing, are extrusions, as you probably already know, extruded steel sections, which are pushed through a die in a molten state, and then the steel it's further processed because it's compacted. The molecules of steel are forced further together by forcing the I-beams or whatever section you are using through wheels that compact the materials, and that can happen. That will happen when the steel is semi-molten, and then it will happen again when it's in a cold state. So what you tend to see very often on construction sites, and you'll be specifying, are RSJs. And again, as I said earlier, aluminium sections, you can achieve a far greater detail. It's still the same process of extruding, of forcing the molten aluminium through a die, but you will get a great deal more detail. And again, just to remind you, when you're drawing sections through buildings, you'll tend to find, it's very easy. I often say to my undergraduate students, you don't need to you render drawings, section drawings, or construction drawings. You don't need to even annotate them, because one knows that a steel joist will take a very particular profile. It tends to take the profiles that it takes because of the actual construction process, and the same for I know for certain that if you're going to draw a section like that through a piece of material at a certain scale, that there is no other material that could be other than aluminium, if it's a continuous edge, which of course it will be. We know it's not going to be steel. You cannot get those perfectly square sections, and also it will not be timber, and I cannot possibly think of what else it could be. Fiber reinforced plastics, possibly, but even then, I doubt if you get such dimensional detail at such dimensions. So there you go. you may or may not be aware, one of the biggest impacts on the construction industry towards the end of the last century was this astonishing ability to bend steel sections. And this was a process that was patented by some people up in I think it's Birmingham, or in the Midlands of England anyway, somewhere in the Midlands, and they patented this process of basically putting steel extrusions through rollers, and they were able to bend, of course, heating them. They were able to bend steel sections, steel extrusions. This is an example, if you like, of how sometimes the construction industry comes up with something that then influences design. Because, of course, once architects and engineers saw that you could bend an I-beam, suddenly you could make an arch with an extreme simplicity compared to all the processes that you would have had to previously use to do such a thing. So a vault, barrel vaults become very practical, very possible. Anyway, this company, the particular company you're looking at here, I think it's called the Angle Ring Company. They do have a patent on this process. Will McLean and I visited the factory many years ago. They wouldn't let us take any photographs, and a funny little aside or an anecdote is that it was, I think, brothers possibly who together came up with the process and then fell out rather badly with each other. So one of the brothers set up a company across the road from this one. So there are two companies in the world that can bend an I-beam for you. One is the Angle Ring Company, and the other is called, I think it's Banshaw's, or Banshaw's is the other brother. But they have a patent over this process. Interesting process. Of course, you can cast iron and steel, which is lovely, but again, quite intensive, quite energy-intensive process to pour molten iron or molten steel into a die. Nevertheless, there are some components, if you like, in the construction industry that that really can't be achieved any other way other than this process of pouring, molding and casting. As you know, with concrete and fibre, anything that can become molten, you can cast into a shape. And so it's a fantastically useful process, casting steel, because, as I say, you could come up with a component like that which you simply could not construct in any other way. You're not going to fold it, bend it, or it's not a fabricated component. It is one object, one piece. Very beautiful, to my mind, anyway. Here's another example of it. This is, as you know, Piano and Rogers building in Paris, and what we're looking at specifically here is these big cantilever brackets that come off the main columns here. One has to say, well, it's another lecture, isn't it? The Pompidou Centre, and I won't go into it now. The Boberg, but anyway, the Gerber, these particular objects again were produced through a process of casting, which is interesting. And there they are, sort of doing the finishing on the cast. Possibly some of the biggest steel casts that we've yet seen in the construction industry. Of course, if you get sheet steel, then, or sheet metals of all kinds, then of course you can process them through CNC cutting. Water jet or laser will achieve the same thing. With steel, you tend to go 10-12 millimeters is about the maximum, because after that it's more a question, it's more the logistics and the time that it takes to cut through that depth of steel that it starts to become rather difficult. But up to a certain depth, it is a practical way of fabricating steel sections. Of course, folding sheet metal is another very important process in terms of components for the construction industry, and we tend the the bench press, which is a mighty weight applied to the sheet steel, using, as you can probably see here, using whatever very particular tools to create the particular shape that you're needing, or the particular fold that you're needing. So these are all, this is in a sheet metal factory. These are the kind of tools that will go onto the end of the bench press to achieve whatever it is that you want to achieve. Again, as I've said to you, I think before, we are interested in you thinking through this process of designing components, or designing buildings, which eventually come down to a series of components, and the processing of the components. You're starting with a piece of sheet metal, a flat piece of sheet metal. You're folding it. You maybe, before you fold it, you will have to cut it into shape. You will have to drill it, perhaps. You'll have to laser cut it. So look at this series of processes. Run the film to the point where you get the object that you want, and then you mass produce that object and you take it to site. One of the most, or some say one of the most important developments in the construction industry, or almost in the history of the construction industry, so in the recent history of the construction industry, is the what used to be called the corrugated iron roof, or the corrugated steel roof. It's a simple sheet of, as you know, of flat sheet metal that has been profiled through this process of rolling. Of course, again, you know already, what the profiling does is to give that sheet a depth, and to mean that it can begin to span where the flat sheet can't. So if you look at the history of simple, cheap roofing materials, this is the one that is most common throughout the world. Even if you have your walls are simple low tensile straw, mud bricks, whatever they're made from, cheap hollow clay bricks, you can get a roof up to a certain it will span a certain dimension with a simple piece of corrugated iron sheeting. So it was a very good idea, and it still is a good idea. Of course, we use it now in a slightly more sophisticated way. We also use it for vertical cladding as well as horizontal cladding. So profiling is an important process. This is a slightly less known process, or these are. I'm going to go through a series of them. They've been more often used in other industries than in the construction industry, but we are looking to use these sorts of processes now. What you're looking at is spinning, which is an astonishing process, still takes place throughout the world. You start with a disc, a flat sheet of steel, a disc. You spin it incredibly fast, and then you sort of work it almost as if you're a potter with a piece of clay on a wheel, and you work into it to get the required shape. And again, there's a whole series of end effectors, a whole series of tools that are used to shape the plate into the required use. So again, it's a small roof, and it has been used for exactly that process. This is wheeling. This is an ancient art, relatively ancient art, of taking a piece of metal, putting it over a die, and working the metal. You're warming it up on the wheel, and you're gradually, of course, it's a craft. You're gradually working the metal into required shape. Again, you start off with a flat piece of metal, and it's very much a handcrafted way of working sheet metal into really quite complex three-dimensional forms. And here's a beautiful example of it. Again, it's a process that's been more often used in the automobile and aeronautical industries than it has in the construction industry. Nevertheless, you can see the product of this process of wheeling, and what is called in the automobile industry panel beating. You take a panel of steel and you beat it into shape. I can't resist in this lecture, since I've diverted into cars, and I apologize for that, but I can't resist often showing this. This is a Bugatti from the 1930s, 40s, I think. Bugatti at that time designed the chassis, they designed the engine, they designed everything that's behind the facade that you're looking at, and then they gave that to two or three what are known as coach makers, coach builders, who then designed the facade that wrapped around it. So what you're looking at here, not only is it's a beautiful piece of, incredibly beautiful piece of panel beating, you can see that there's a standing seam here, which again is very popular way of in architecture of solving the use of cladding buildings, the standing seam, so it can be split along that edge, which is rather nice, isn't it? This particular design, forgive me, I can't remember who the coach builders were of this particular design, is still to this day, which where are we, 2021, still the most expensive car ever sold at auction. So the modern version of panel beating, wheeling, etc., is what is known as incremental sheet forming, specifically SPIF, single point incremental forming. The reason it's called single point is because that rather complex piece of geometry that you're achieving here with a piece of what was originally a piece of flat steel is achieved through the end effector of normally at least a probably 5-axis robot, possibly a 7-axis robot, with a very particular end effector, which will do so you're working into it in a funny way, much the same way as they physically worked into a piece of steel when they were spinning steel. Here you're using the robot to profile the steel for you. Now, you all know that you do have at the Marylebone campus, if you have access to them, you have two 7-axis robots at the Marylebone campus, so I would greatly encourage you to look at this process and see what you might be able to achieve with it. Okay, so I think that's the state of the art with how we manipulate certainly sheet steel at the moment, or sheet metals. Could be aluminium again, could be a sheet of aluminium which would be softer and easier to work. So to begin to wind the lecture down, I just want to show you a few case studies, and some of these I think towards the end are lectures in themselves. So I'm just going to make a reference to them, and we will expand. Well, they are expanded upon in a series of lectures that we call Building Systems, that we will get you access to. We probably won't have time to run them all this semester, but we will give you access to. So what are we looking at here? We're looking at the inside of a hot air balloon. Well, not a hot air balloon. It could have been helium or it could have been hot air, but it's effectively an airship. Of course, it demonstrates a number of things. It demonstrates how beautifully delicately you could put a structure together, if you have elements that are in pure tension. Of course, elements in pure tension will always make the structure lighter. It's a more complex way of putting buildings together. Look at the work of Fry Otto and his tensile structures. Look at the Munich Olympic Stadium that he built, and many other examples of putting buildings together in pure tension. So again, we'd encourage you to think about this because of the way you minimize the use of material, the general lightness of construction, which makes it you're using less of the world's resources and you're using them, I think, more efficiently. Of course, excuse me, this one will be skinned. This will have an envelope that will to some extent act with it. So they are semi-monocoque stressed skin structures, the airships. Nevertheless, I'm showing you this because again, it's a steel frame. It's what we would call a habitable truss. Willie Alsop, may he rest in peace, one of the great individual architects of the last century and latterly in the early part of this century. So there it is. It's a big habitable truss, isn't it? And that's when steel can be fantastically efficient, because you can't imagine any other way, logistically, apart from structurally, logistically of putting a building together on top of another building, unless you could make a fairly delicate, relatively lightweight frame that you could then hoist into position, as Will did in this project. At the other, well, sort of the other end of the spectrum, again, it's a wonderful material for making, generally delicate, lightweight structures. So here again, we're using trusses, aren't we? We're using it's the crane, sort of three-dimensional trusses that are just carrying again a profiled sheet. In this case, profiled roof. In this case, it's polycarbonate. It's clad entirely in polycarbonate, so it's kind of a nice combination of plastics and metals. Does the job. You can see that there's internally there's bamboo, which is controlling the amount of solar radiation into the buildings, and of course to giving you a certain amount of privacy. Simple structure. I'm showing you this again. This is an interesting place to visit if you do get a chance. You'll be looking at that and thinking, well, this is all quite old technology, and you'd be right. But the technology, two bits of technology you're looking at the moment. One is the airplane itself, of course, and the other is the shed in which the airplane is housed. And just to emphasize, okay, two things. The airplane, this is a lattice structure. This is a monocoque structure, of course, because the skins, they've kindly sort of cut away here, is part of the overall, gives the tensile strength to the overall structure. But this lattice, this delicate aluminium lattice, is incredibly strong and incredibly light, and it's as good a way of putting anything together now as it was then. The other thing you're looking at here is a beautiful portal frame roof, again with a series of trusses which are triangulated, a little bit like the boom of a crane, aren't they? And what's interesting about the Brooklands Museum, and it's out in West London off the A3. I hugely recommend a visit because there's some wonderful things to see there. But this building, even the building itself, was at some point completely disassembled, all the parts of it, because it was a building that was capable of being done to it. It's bolted, so not welded, of course. It's a bolted steel structure, completely disassembled. All the parts were refurbished and put back together again. So you're looking at sort of a relatively new building made from bits and pieces that are, 50, 60 years old at least. So it was reassembled. Now that's interesting. That is also interesting because, as I said to you, I think at the beginning of the lecture, steel particularly is a material that we will probably, I imagine in your lifetimes, we may stop mining it, or we may stop mining iron ore because of its the inefficiency of the amount of energy that's used in the process. But there's an awful lot of steel on the planet that can be reused or recycled. So if you're designing for a certain life, you think about how you put a building together. How easily is it demountable? Is it disassembled, if you like? So this was the Brooklands Museum. So lovely details, as I say. It's a lovely, again, not big extruded eye sections, small sections put together, again very delicately, to make the portal frame. And what are we looking at? Of course, a nice simple corrugated cladding. Here's the again going back to the aluminium lattice work for the fuselage of the airplane. Again, another beautiful way of putting structure together. This is actually a slightly more modern airplane fuselage, which is steel. Actually, I'm not entirely sure. I think it probably is. It looks like it, doesn't it? Might be a lightweight steel structure. But we borrow from other industries. We've always done it in architecture. The reason we've done it is because the industries that we borrow from, aeronautics, automobiles, yacht design, these are industries that by nature require efficient use of materials, and they require lightness. And architects, as I say, have always looked to borrow from these other industries, and we will continue to do so. We will look for efficiency, we'll look for detail, and I will give you some more examples later. In fact, here's a rather nice one. This is the Lord's Media Centre, as you can see. Again, this is just up the road from the university, just a little bit north of the Marylebone campus. This was designed by Jan Kaplicki. May he rest in peace. Of Future Systems. It is an all aluminium monocoque structure, and it was built by shipbuilders because that's their speciality, if you like. They're familiar with this process. It is a kind of yacht hull, isn't it? If you look at it, if you think about it. It's also all prefabricated off-site, so it was all built somewhere up in, it could be Tilbury, somewhere up the River Thames. I'm not quite sure how far up the River Thames. It was built in sections that were big enough to be just not too big, that could be shipped down the river as close as we could get to central London, and then taken up to Lord's Cricket Ground and hoisted into place. So this is a monocoque, again, a stressed skin structure. As I said, it's similar to the way you would put an airplane together or a boat together. Often there's two skins, there's one on the inside and the outside, but as you say, it's a fairly simple orthogonal lattice structure. That's all aluminium. Well, the skin, of course, is taking all the it's taking all the tensile loads, the lateral loads. It's locking the whole structure together on the outside, isn't it? They mocked it all up, so they kind of spot welded the whole thing in a warehouse just to make sure that it would all work, which is rather nice. It's a shame because if you are in the university, there's a filing cabinet outside our office on M501 that has some of the original drawings of sections through this building, which are rather interesting to look at. So that's an all aluminium monocoque structure. This is a lightweight steel structure designed by Niall McLaughlin and engineered by Price and Myers, another very interesting group of structural engineers. Price and Myers was built some years ago. They were commissioned. Niall McLaughlin was commissioned to design this footbridge across in Bristol, and he said something like, "Well, wouldn't it be nice if it was virtually invisible, like all architects do?" And they thought about making it out of glass. They thought about making it out of polycarbonate. They showed a kind of general design principle. You can see a very gentle, probably part of an ellipse curve, which it needed. Price and Myers said, "Well, what if you made it out of steel or some kind of lightweight steel or even aluminium? Folded metal is a good way of making efficient structures. And what if we perforated it so it was almost see-through?" So what we're doing here is that what they decided, you can see, is tiny perforations throughout the structure. We're taking as much weight away as we can without the structure losing any integrity. So of course what we've got here is effectively two trusses. These are folded sections, as you can see. That it's the depth, of course, it's the span to depth ratio is working. But instead of actually making a truss, typical truss, or even big circles, big perforations, we're going to do lots of tiny perforations. And what we'll do is we'll do a finite element analysis of it. And I apologize, I used to have the image of their FEA of this particular bridge, and what it begins to show you, where the stresses grow, we'll stop perforating it. So of course here the big stresses begin to occur at these edges here, and so it's less perforated towards that was the rule. We'll keep exactly the same grid everywhere, and we'll just take holes out where we need more stiffness and strength. And they did that throughout the whole structure. So two very good principles at work here. Folding metal rather than sort of extruding it, rather than using great big I-beams or anything else like that. We're using the stiffness. We're making stiffness through folding the metal, thin sheets, and then we're perforating it to take even more mass away. And this is the sort of thing that Michael Schleich is doing. Same kind of principles. It's very beautiful bridge that he made not so long ago. These have been laser cut, folded. The processes we were looking at earlier on, completely prefabricated off site, shipped to site, and light enough to be able to solve all the problems. So what we're looking at here, a kind of lovely, beautiful combination of an efficient geometric shape, efficient structural logic, if you like, efficient use of the material, and just using it by folding and bending. So that's very beautiful. Again, very beautiful project. Prouvé was doing this back in the 1950s because he was by trade a sheet metal worker, making furniture and other things, when he began to branch into system building and was approached by I think it's Corbusier, or certainly Jean Aurault, and he developed astonishing things like this, like the Le Pavillon Démontable. But again, this is another lecture all on its own, and again I will reference you to look at the system buildings of Jean Prouvé. Similarly, in a different, very different, but much more modern way, Adam Kalkin is working with developing or refurbishing shipping containers. Let's use what we've got in the world. We've already built a huge amount of things. These are just otherwise they'll be just completely wasted. They'll be rotting away somewhere. We have this resource. It's part of the principle of recycling. It doesn't mean, like all system building, if you like, it's not telling you as architects how to design. The innovation comes in what you do with the product that you've got. This is not about taking the fact that it's a system or it's modular in any way. It should not deter you from looking at these systems and thinking, what could I do, or how could it, or it might even be some part of your design thinking. I've got a good example of it, and I'm not sure that I have it here. I probably don't. But again, if any of you live in South London, you might want to pop down to the Herne Hill Velodrome, and you will see a lovely little Hopkins development where they've used containers shipping containers, and put a lovely little tensile roof. They've put them in a kind of designed them around a forecourt, an open area, and then put a little tensile roof and linked them all together. Anyway, so here's again. This is going to be another lecture on its own. That's Fritz Haller on the right with his MIDI system. A very interesting, very efficient way of putting structures together. That's Konrad Waxman on the left, by the way. Fritz Haller's system is still used to this day. It's a little bit like I think we talked about Walter Siegel when we were looking at timber. It's that's another lecture on its own. These guys, they were working, yes, admittedly towards the middle of the last century, working with innovative materials, but the principles of what they were doing can still be applied. In other words, in terms of Fritz Haller, you can now get software. One of the things he was very interested in was integrating services into structure. So you can now get so he's not saying you use this, that, or the other particular component. He's saying here's the principle of how we might logically put buildings together efficiently with metal frames of some kind or another. And here's it's software. It's not designing for you, if you like. Excuse me. So that is Konrad Waxman. Sorry, I did that I did think it was the last slide. I was just double checking. That's Konrad Waxman showing what you could do with space frames, or what the Americans call space grids, using, again, just connecting simple steel components or aluminium components. components together. It's scaffolding, what we call scaffolding, on a very grand scale. So as I say, yes, look out for for various other lectures on system building using steel and aluminium frames. Okay. Thank you very much.